Okay, so hello everyone. My name is Noran Shahin, and I'm presenting from the University of Houston. It's connected to the research that we did in the previous first presentation in this session. And I'm going to be presenting about the soft and membrane model and its potential for use in UHPC. So first, I want to go over an overview of the model. So first of all, the concept behind it, the motivation, it comes from the concept of being able to characterize structural behavior of a structure based on its component materials, and this is very useful for reinforced concrete because it's very complex to assess the structural behavior. Given that it's very heterogeneous. And the idea behind the panel tester is that you can characterize an element behavior and kind of treat the heterogeneous material as something that's continuous. And so that's the potential behind this model, that it allows you to characterize a structural behavior by characterizing an element of that structure subjected to any stress state, and using that in finite element frameworks to be able to assess the structural behavior. And so the assumptions behind the model is that your reinforced concrete, or your UHPC in this case, is one continuous material rather than comprised of the constituents, and that your equilibrium equations can be based on the fact that whatever stresses you have in the element are just the sum of the stresses in your concrete matrix and the stresses in your reinforcement matrix. And another assumption that's made is that the reinforcement can only take axial stresses. And finally, this is a fixed angle theory, so it's based on the fact that the equilibrium equations are derived from the principal axes of the element that you see at the left. And then on the very right, you can just see an example of the model and compared to experimental results of panels tested in pure shear. Okay, so the components of the model. The model has, the basic components of the model are the equilibrium equations, compatibility conditions, constitutive relationships, and obviously that you know what stress state your element is subjected to, right? So whatever stress state you're trying to investigate, whether it be pure shear or shear combined with axial effects. And so the model equilibrium equations and compatibility conditions don't vary based on the material that you're dealing with, but what's very important to take into account for UHPC is the constitutive relationships in the model, which need to be further developed and investigated for UHPC, given that it's a very new material. And so as the flow chart that you see on the right shows how the governing equations are solved and how different components fall into that iterative procedure for solving for the shear stress strain behavior of the element. And what we really want to investigate for UHPC is how we can characterize the constitutive laws so that we can be able to predict the shear behavior of UHPC elements using this model. So this is just an example of characterizing the compression constitutive behavior of UHPC panel elements. And so when in a panel element, you have in-plane stresses in a 2D state. So you have to account for the softening of the compression stress strain behavior due to the effect of tension compression by axial stress state. So these curves show, using experimental data from the University of Toronto panel tests, we developed some methods for characterizing the softening behavior and the compression uniaxial constitutive law. So based on our analysis of the softened membrane model, we observed that the shear stress strain behavior of a panel element is largely dictated by the tensile stress strain behavior. So although we did some investigation on the compression stress strain behavior, the softening, and the Poisson ratios of the element, we found that what mostly governed the shear behavior was how we define the tensile stress strain behavior of the UHPC matrix, and so it's very important to further investigate this. As you can see on the very right, it shows a shear stress strain curve for a panel element, and which is the blue curve, and then the brown curve, you can see that it's the tensile stress strain of that same panel element. So it's the principal tensile stress versus the principal tensile strain, and so you can see that the behavior is very similar, as well as the ultimate in cracking points. And so it's very important that we kind of investigate how we characterize the shear stress, the tensile stress strain behavior, because according to this model, you can see that the shear stress strain behavior is highly dependent on that. So just before we go into further characterization of the tensile behavior, you can see the model predictions, or what the model gives for different stress and reinforcement configurations. So these are panels tested in pure shear at the University of Toronto, and you can see that the model, based on the material testing characterization, you can see what the model can predict. It's not entirely accurate for all cases, especially the third specimen, which is unreinforced. But the general behavior is very similar to what we would see in the tension. So in order to further assess the ability of this model to predict or to capture the experimental response of elements tested in shear, we performed a statistical analysis to see if we can capture this response. And so we used the results of direct tension tests, or actually in this case we used the results of the material tests that were done by Toronto for the same panels, and we used the statistical parameters, namely the mean and the standard deviation, in order to run the Monte Carlo simulation. And so, and assuming a normal distribution for all of the variables involved. So the variables that we're investigating are the tensile cracking stress and strain, and localization stress and strain. And so using the statistical parameters for these, you run a high number of random trials, and you obtain an envelope of further results. And so as you can see, the envelope is rather wide, varying different parameters, due to the fact that there's high variability in the material tests performed. So your material tests kind of give you a high range of variance, a high coefficient of variation, in terms of like the cracking stress and localization stress and strain. And so this end result gives a high range of prediction for the model, which doesn't really give very conclusive results. So what we investigated again was, maybe rather than just using the material tests done for those panels, which weren't very large in number, we took a look at a larger data set of material tests done to characterize tensile behavior of UHPC, and we used an average variation for each parameter. So rather than using just the variation from a series of 6 tests, for example, we'd use an average variation from several series of 6 tests, maybe like 100. So you can see the variation slightly lower, but still relatively high. And just so you can kind of get an idea of how the variation of the tensile parameters affects the model prediction envelope, you can see that assigning it a variation of 10% gives you a rather narrow envelope. And so what we had before, because we have high variation, there's a high prediction range. Okay, so some conclusions that we can make are that the soft memory model, it provides a good means to predict the shear behavior of UHPC. However, more work has to be done to assess how we can go from a uniaxial tensile stress, tensile stress strain behavior to structural behavior in tension, because it's not exactly linear. You can't exactly say that the uniaxial tensile stress strain behavior is exactly the same as the biaxial stress state, and so more factors have to be taken into account. And then continuation of material characterization efforts. I feel like this is something that's kind of very big right now in terms of UHPC characterizing the tensile behavior using different tests. There we have direct tension tests and other tests, the punching shear tests to characterize the tensile behavior. And so further work needs to be done to kind of assess the probability distribution of the different parameters, like the tensile cracking stress and stress strain and the localization stress strain, to see like what variability do we have, what kind of distribution do they follow. Maybe they don't follow a normal distribution. That was just an assumption that we made. And then assess the difference in the results given by different test methods for tension. And then finally, use the predictions from this model, once validated, can be used to assess the concrete contribution in resisting shear in various structural members. So you can predict your VC component in your shear design equations, and also it can be used in finite element framework to predict the shear response of structures with UHPC elements. And then I would like to give some acknowledgements to both PCI and ACI for providing funding for this research. Thank you very much.